Hey guys! So this is our lesson, our first lesson in the polynomial unit probably. We're going to be doing polynomial operations. So some of it's going to seem really obvious and simple and some of it gets a little tedious. So hang with me. First we're going to be doing the basic operations of adding and subtracting. So your setup of your problem is up to you, and if you're lazy like me, you're not going to take the time to rewrite the problem. So if it happens to be written vertically, that's kind of nice because everything's lined up beautifully, which makes your life a lot easier. So for instance here, your like terms are already lined up. So negative 7 plus 8 would combine to a positive 1. Negative x plus nothing is a negative x. 2x squared plus negative 10x squared is a negative 8x squared. And then 3x to the third plus 1x to the third is 4x to the third. And it could be as simple as that. So what made that problem so nice is the fact that the terms were all lined up. So you could collect your like terms easily. But this is usually how they're written, horizontally. So you have to kind of go through, and you know I love using colors, so I go through with colors and kind of collect my like terms that way. So there's only one cubic term, so 9x to the third. But if I keep looking, next in line for standard form would be the quadratics, the x squareds. And I only see one of them, and we're adding 5x squared. And then we have some linear terms here. We have negative 2x, and then remember you're adding a 12x. That would be a plus 10x. And then finally the constants. So you have a plus 1, and then careful, plus and negative 4. Use your calculator to double check when you're taking a quiz on this, right? So that's a negative 3. So you're still going to get the right answer. You just have to be a little more careful about like term collection. And always anytime there's a negative, you got to be careful. Now subtracting, you got to be extra careful because even if it's lined up with like terms, you have to remember that you're subtracting. So like for instance here, what I like to do, they put parentheses around it, which was smart. But a really large negative sign or subtraction sign, so that way I remember what we're doing. So 9 minus 1 would be a positive 8. Careful here, negative 2x minus the negative 1x. So that double negative becomes plus x. So negative 2x plus 1x is a negative x. That was really confusing, right? So negative 3x squared minus 6x squared is negative 9x squared. I know I'm not really lined up anymore, but that's okay. And then 8x to the third minus 2x to the third is 6x to the third. So again, it helps that the like terms are lined up, but actually in subtraction, I almost don't like it better because I wish I would just distribute the negative, which I'm going to do on the horizontal method. So what I mean by that is I like the parentheses, I like the negative sign out in front. What I don't like is having to remember to distribute negatives because negatives are places where we mess up. So you can actually lose the parentheses and then just have a combining like terms problem once you do the distribution. So this is still 2x squared plus 3x, but then this becomes a minus 3x squared, and then a minus x, and then this last term becomes a plus 4 because of the negative negative. Now I'm going to go through and collect my like terms. So I'm using my colors, 2x squared minus 3x squared is a negative 1x squared. And then what else we got here? We have linear terms, we have plus 3x, and then a minus 1x, that would be a plus 2x. And then finally, there's a constant over here, which we now know is a positive 4. So oddly enough, I actually prefer the horizontal method on the subtraction problems because I'm going to take the time to distribute the negative because I know that's a place where I make a mistake. And again, I'm so lazy that if it's not written that way, I'm not going to take the time to rewrite it probably, so I'm just going to do whatever method is there. So this is a multiplication problem. This is not an x, but a multiplication sign. And if it's stacked up vertically, it's kind of nice. It resembles like when you were little kids and you were doing multi-digit multiplication. And you just kind of distribute the terms to everybody in that format. So this negative 3 is going to get multiplied by everybody in the top polynomial here. So negative 3 times 4 is a negative 12. And then negative 3 times 2x is a negative 6x. And then negative 3 times negative x squared is a positive, which I'm actually going to write down a positive sign, 3x squared. So now we do that same thing with distributing the x, and it's going to go to everybody in the top. But when you were a little kid, remember how like you put a placeholder of 0 and then it bumped everything over so you were multiplying by the proper digit? Same idea can happen here. You can put a 0 here if you want as a placeholder, because what happens is now the like terms will be lined up. So x times 4 is a positive 4x. And then x times 2x is a positive 2x squared. And then x times negative x squared is a negative x to the third. There's no like term there to collect with that one. Whoops. Okay, get my face out of the way. Try that again. All right, so now you add up the like terms, through the columns. They're already lined up. So negative x to the third plus 5x squared. I almost said 6. Goodness. All right, and then a minus 2x. And then negative 12, minus 12. So there's your product. And the idea was we distribute it, which is the same kind of format and setup as when you were little. Unfortunately, the problems are very rarely written that way. They're usually written horizontally, but the idea of distribution is still the same. You're still going to take the x and you're going to multiply it to everybody in the other polynomial. So you can kind of sense it's the exact same setup. So x times 3x would be a 3x to the third. X times negative 2x is a negative 2x squared. And then x times negative 4 is a negative 4x. Just go slow on your distribution because it's easy to screw up, right? Now this time you have a negative 3 that you're distributing. So watch your signs. Negative 3 times 3x squared is negative 9x squared. Now rather than writing a long line here, I'm just going to place it underneath the other x squared term. That way I have that nice like vertical, everything's lined up for like terms. Negative 3 times negative 2x is positive 6x. And then negative 3 times negative 4 is a positive 12. There's no like terms for the constant. So now everything's lined up. Look at that. So dropping everything down and collecting, we have 3x to the third. If you add these together, you have a negative 11x squared. And then you have a positive 2x, and then a positive 12. I really like when those are stacked vertically once you are writing down your work. A kid taught me that trick actually one year, a long time ago, but I loved it and I've used it ever since. This problem, I made a face because it's actually a really bad problem. So when you have 3 binomials multiplied together, you can't multiply all of them at the same time. You have to kind of do them in stages. So step 1 is choose 2 of your things and multiply them together. And usually I look for the easier thing to multiply together. It turns out there's no easy thing to multiply together here. So I'm just going to multiply these together first. And what you end up with is a distribution problem or a FOIL problem, right? We have x squared. Now this term is plus 3x, and then this would give you a plus 4x. You can say plus 3x and plus 4x, but I'm a little worried about like how much work I have to write down. So I'm capable of just go ahead and adding those in my head and saying it's plus 7x in the middle. Especially with all the factoring we did last semester, right? We're pretty good at those arches. And then here we got a plus 12. Now if you have plus 3x plus 4x and then take another line to add them up, totally fine. The problem is we're not done. We still have this x minus 1. Here we go. Now we have to do like the last problem. So we're going to start with the x and we're going to distribute that to everybody in the other polynomial. So that gives me an x to the third. So x times x squared is x to the third. X times 7x is plus 7x squared. X times 12 is plus 12x. So negative x squared, and then let's see, negative 1 times x squared is negative x squared. Negative 1 times 7x is negative 7x, and I'm lining them up again. Negative 1 times 12 is a negative 12. So everything's all lined up as far as like terms go. Now I just have to collect them, and we end up with x to the third. Let's see, that's plus 6x squared plus 5x, and then a minus 12. I think you know this about me by now, but I love using colors in math. I love when you guys use colors in math. I think it really helps organize your work and you can kind of see where things come from. It just makes me happier to look at it, frankly, especially those of us who have kind of negative feelings about math. And I know that's a lot of us. Just using colorful pens might brighten your spirits a little bit, I guess. I don't know. I don't know about you, my memory's pretty shot these days. So when they give me a pattern and they're like, why don't you memorize this pattern? I'm like, oh, I don't want to. So turns out we don't have to memorize these patterns. And the more you use them, you might kind of stumble upon the pattern yourself. So I actually don't bother with these patterns at all. And I just say, what is this problem really asking me to do? X plus 2 squared is just x plus 2 times another x plus 2. So it's really just a distribution problem that we've been doing this whole time. So x times x and x times 2. And then same idea, the 2 times x and the 2 times 2. So I could have probably collected those like terms in my head like I did on the previous question, but we end up with a product of that. So when I look at this pattern, which that one right here was this pattern, it says, you know, the first thing squared plus double of the arches, which, yeah, that's what happens. You have an arch, and they're the same thing, so you double them, and then the last thing squared. So I don't know how groundbreaking those patterns are to memorize. Oops, I have a whole other problem to do. I think it's just easier for you guys at this point, especially with us all being kind of limited with brain capacity these days. I don't know about you, but I'm tired, guys. And I surely don't want to memorize things I don't have to memorize. All right, so I'm just going to write it twice, and we're going to distribute. Now be careful here. We have 3x times 3x. That is a 9x squared. And then 3x times negative 4 is a negative 12x. And then guess what happens? This next arch is the exact same thing. So it's another negative 12x. And then a plus 16. So there's that double the arches going on in the middle. This time they were negative signs, so it's negative 24x plus 16 on the end. So if you just love memorizing math patterns, add those to your repertoire. I obviously have them memorized because I'm old and I've been doing this forever, but now this one, again, I don't think most kids look at this and think this looks like a good time. If you move on to pre-calc and calculus, you probably want to get this memorized, or there's something else called, bug on my screen, Pascal's triangle, and you can figure out a way to expand a polynomial that way. But for now in Algebra 2, I think it's just easier for us if we just say, you know what this really says? It's a 2x minus 5 times another 2x minus 5 times another 2x minus 5. Now, if you can think back a few problems, you're going to remember this is not exactly good news. This problem is not simple. And obviously, if I look at this pattern, like nothing about that looks simple. So if we're doing this kind of the long way, it's gonna take a few lines of work. That's why I gave you so much space. So first thing I have to do, all right, so we're foiling this one together. 2x times 2x is a 4x squared. Now, this one might be a little trickier unless you remember the pattern we just looked at. We're going to have a negative 10x, and then we're going to have another negative 10x. So if I double that, that would be a negative 20x in the middle. If you got to write that out the long way, it's totally fine. And then negative 5 times negative 5 is a plus 25. All right. Where's the other guy? So we have another 2x minus 5 that we now have to distribute to all of that. So this is where, yeah, it gets a little lengthy. All right. Carefully distribute the 2x to everybody into the blue polynomial. So 2x times 4x squared is an 8x to the third. 2x times negative 20x is a negative 40x squared. 2x times a 25 is a plus 50x. Now the fun keeps going because now you got to take this negative 5 and distribute it to everybody. So I'm going to use that trick about lining up the like terms. Negative 5 times 4x is negative 5 times 4x squared is negative 20x squared. You'll kind of notice a system where like they move down in degree as you multiply, and then when you go to do the next line, it usually starts at the second term, right? It depends. As far as Algebra 2, pretty much all of our problems look like this. So negative 5 times negative 20x is positive 100x. And then negative 5 times 25 is negative 125. Obviously, you'd be using a calculator if you weren't sure about those math facts off the top of your head. So when I combine all my like terms, I have 8x to the third minus 60x squared plus 150x, and then minus 125. That was a hoot, right? So that problem at the beginning ended up expanding to a very elaborate product, and it really wasn't as simple as it first looked. That's the unfortunate news about math. That's kind of how it works, right? All right, one more question, then we're all done. This is an application of polynomial operations, and this is a profit question. So we're trying to raise money for a trip to Spain, and we're going to sell cookies. So there's some clues about revenue. So revenue, I need to grab some pens here. Revenue, highlighter, is money that you're taking from the customer. So revenue from selling X cookies is right there. So that's money from the customer. You put it in your cash drawer or whatever you're collecting money in. But then there's cost. So to either buy the product or make the product, there's going to be a cost associated with that. I'm going to highlight that in fuchsia. So the cost for making X cookies is given by this equation. So then we're like, well, what's the profit? That's what the real question is here. So what are we selling each cookie for? They want to know how much money we're like going to take from the customer when they buy a cookie. And revenue is what we take from the customer, right? So you need to be looking at revenue. So right here, it's 2.5 times every cookie. So that must mean that we are charging the customer $2.50 for each cookie. That must be an amazing cookie. Better be for $2.50. All right, let's talk about profit. Profit is like the term net in business. So you take what you're taking from the customer. So you take your revenue, and then you're going to subtract any cost because you had to pay for the product or you had to make the product to begin with. So your profit function, which we will call P of X, is found by taking your revenue function, which they called R of X, and subtracting your cost function, which they called, let me guess, C of X. Now what you might want to do in your notes is put a parenthesis set around the cost, because anything that we had to pay for has to be subtracted out of the revenue. So if you're like renting a machine, paying somebody to cook the cookies, if you're paying a rental space for the kitchen, everything has to be subtracted. So for our problem, the profit function, I don't know, but the revenue function, I super know, it's right there. So that's 2.5x. And then we're subtracting the cost function, which I'm going to put in parentheses, which is this guy right here, x plus 32. Now, you know it, we got to clean this problem up. So your profit function, and I distribute that negative, you get 2.5x minus x, and then careful, minus 32. And if you keep cleaning that up, you're going to get 1.5x minus 32. There, children, that is your profit function. So we're really only making like $1.50 off of each cookie after we pay off these $32, which maybe that was for like, I don't know, ingredients or something. All right, what's your profit for selling 381 cookies? Well, that's pretty easy for us to find. Now that we have the profit function, you're just going to plug that in. I don't have a calculator. Uh-oh. So I got to pull up my calculator. Where'd he be? I already forgot what the problem was. 381 cookies, $1.50, x minus 32, I think was the function. Can't believe I forgot to bring my calculator. All right, $1.50 times 381, and then we had to pay off that $32. $539.50. I don't think we're getting to Spain on that, but you know what? It helps every little bit. Oh, jeez, I should quit today. I forgot what it was now. $539.50. See, this is why I like to teach the lessons live to you guys, because $539.50. Okay. $539.50. So that's definitely not the amount of money that I have sitting in my cash register after a day of selling cookies, because we had to take off all that cost. Okay, so that's your lesson on polynomial operations. Like, the concepts weren't crazy, but the articulation of them is, you have to be really careful and meticulous. Negative signs mess with us. We have a combination of adding and multiplying, and does x become x squared when you multiply? Yes, but it doesn't become x squared when you add. There's a lot of like under layers of math that we got to be careful about in this lesson. So just go slow, use your colors, make your math happy today, okay? All right, good luck everybody. Let's see if I can figure out how to stop my video.